Okay, so we ended the last lesson with a little reminder that the probability of E intersect F does not generally equal the probability of E times the probability of F. Okay, that only works if E and F are independent. Okay, so this rule that you might kind of vaguely remember from a statistics class that wasn't super careful about independence assumptions doesn't generalize to cases where the events are related to each other, but that really should be no big deal because we do have a way of finding the probability of the intersection that always works. We have a way of finding the joint probability that always works, and it just comes from rewriting the definition of conditional probability. Okay, so reminding ourselves of that definition. The definition of conditional probability says probability of E conditional on F is the joint probability of E and F divided by the probability of the conditioning event here. Okay, well, just very easy to rearrange that as the probability of E conditional on F is the probability, I'm sorry, I wrote the right thing, but I said the wrong thing. The probability of E and F, the thing that we're looking for in cases where E and F aren't necessarily independent. What is that? That is the probability of E conditional on F times the probability of F. Okay. So this rule always works. If it happens that E and F are independent, then this will be the same as the probability of E. And if they're not independent, you're using the right probability, not the wrong one there. So great. This also generalizes. So if we want something like the probability of E intersect F intersect G, okay, that is the probability of E conditional on both F and G times the probability of F conditional on G times the probability of G. Okay, and you can have as many chains as you'd like in there. In the notes and right here, I've got a bigger tree that corresponds to the case of three events, E, F, and G. And it's big enough that it's kind of a hassle to draw. So I wouldn't try to draw it freehand if you're taking notes. You can get this picture from the website. But as with the two-event tree that we looked at in the last lesson, we first find out if we're in the world of E or the world of E complement. If we're in the world of E, then we go down. Are we in the world of E and F or E and not F here? If we're in the world of E and the world of F, then what's the probability of G conditional on those things? And the way to get the joint probability is to multiply the edge probabilities here. Okay, so the probability of E times the probability of F conditional on E times the probability of G conditional on F and E here. So, whichever letter represents the top of the tree or the bottom doesn't necessarily matter. What matters is that you're conditioning out the things that you know here. Okay. I think I want to go back actually to the smaller tree, the tree with ideologies in it, where you had probability of being liberal here, and then if we went down this part of the tree, on the next set of edges, we had the probability of being progressive, conditional on being liberal, the probability of being traditional, conditional on being liberal. If we didn't go down the L branch here, we went down the C branch. C is the complement of L. If you're not liberal, you're conservative. So probability of being conservative is there, and then we would have the probability of being progressive, conditional on being conservative, and the probability of being traditional, conditional on being conservative here. And again, if we multiply these probabilities here, multiply the probability of being liberal times the probability of being progressive, conditional on being liberal, what do we get? We get those joint probabilities. So just very first thing I wrote, I'm saying it in a different way here. So this is the probability of L intersect P. This is the probability of L intersect T. This is the probability of C intersect P, and the probability of C intersect T, close my parentheses there, okay? And those are all calculated using exactly that rule that, that I had just written, okay? That it's the probability of L times the probability of P conditional on L. I'm writing it in a different order because this is sort of the order that makes sense with the logic of the tree, but these are just numbers. So of course we can switch the order of multiplication. Okay, so that's what we did before. And so we're using actually all the time this general rule for the probability, for a joint probability that's a conditional probability times the probability of the conditioning event. Conditional probability times the probability of the conditioning event. That's the right way to calculate a joint probability. The other thing we can do, and I can't remember if we did this in the other lesson with a tree or not, but we can calculate, you know, what we would call the marginals if it was crosstabs. We can calculate something like the probability that you're progressive here. How might I do that? Well, I might notice that there's two ways to be progressive. Okay, you can either be progressive and liberal or progressive and conservative. So the liberal conservative partitions the sample space, also partitions the event P. So this is the divide and conquer rule for sets. I can divide up P into P intersect L and P intersect C. And since L and C are mutually exclusive, their intersections with P will be mutually exclusive, so I can just add up these probabilities. Okay. Put that a little bit neater there. That is the probability. So if I want to know the probability of P in this, with these particular numbers, I'm trying to remember what the numbers were in the last lesson. This was 0.32, and this was 0.18. Okay, and that gave me probability of P equals 0.32 plus 0.18 is 0.5. Okay. We got that in the crosstabs as well. So we've been doing this kind of, you know, going back and forth from total to conditional to joint, just keeping straight which is which. We can generally convert them to each other. The thing that I want to elaborate on right now is this. Okay, so I think I want to go to another page. This is getting kind of crowded here. So new page, and let me go back to my E's and F's here. Okay, so the probability of E is the probability of E intersect F plus the probability of E intersect F complement. Same deal. Okay, we can partition E using the divide and conquer rule for sets in terms of any other set and its complement, and then we get, because it's a partition, we can just add up the probabilities. Fine. How do we do that in the tree? Oh, how do we calculate the joint? It's the probability of E conditional on F times the probability of F plus the probability of E conditional on F complement times the probability of F complement, which is of course 1 minus the probability of E. That is kind of the short version of the law of total probability. Super duper useful. The way many people, me included, think about the law of total probability is that it's a weighted average. What's the probability of E? Well, it's some mixture of the probability of E if we're in the F world or the probability if we're in the F complement world. What determines how much of this is in the mixture versus that? Well, how likely are we to be in this world versus that world? Okay, so you're taking the conditional probabilities, weighting them by the probabilities of the conditioning event, and adding them up to get the total probability there. Super duper useful. And let me give you kind of the long version here. This is, I would say, the short version. The long version. It's long just because it's a different kind of partition of E. So if F1, F2, Fn, partition S, actually, or if E intersect F1, E intersect F2, all the way down to E intersect Fn, partition E. The thing in red could be true without the thing in blue. If the thing in blue is true, the thing in red will always be true. So if either of those things are true, then we can divide and conquer the probability of E in terms of how likely is E in the world of F1 times how likely are we to be in the world of F1, plus how likely is E to happen in the world of F2 times, well, how likely is F2 to happen all the way until the probability of E in the world of Fn times the probability of Fn. So again, a weighted average, what we're taking the average of are the conditional probabilities, and the weights are the probabilities of the conditioning events there. So rather than just continuing to assert, although it is true, that the law of total probability is super useful and cool, the next lesson will show you an example of it being both of those things. So I'll see you then.